So we're working through these concepts involving parametric equations. And really the only thing different here is we're introducing another variable, time. And this will allow us to solve for problems like projectile motion. And when we get to vectors, we're going to have that time component as well. But even with this third component with time, a lot of our concepts will still remain the same. The way that we find derivatives, the way we find integrals, even arc length that we're going to see, there's going to be a lot of similarities. So even though we have this additional time component, a lot of these processes will feel familiar from what we know with derivatives and integrals. Okay. So let's okay. So just wanted to review arc length for a function, and then we can adapt for parametric. So f prime, we can think of f prime as, if we were to break this down into parametric form, it's basically y prime over x prime. So just want to show how this is going to get derived into this arc length formula for parametric. Okay, so imagine taking this piece here and extending it into parametric form. So f prime in parametric form will be y prime over x prime in relation to time. And then if we were to break this into common denominators here, it will look like dx dt right. We're just making that one into something that can share denominators. And if we were to flip that denominator up, again, we don't have to worry about how to derive this every time. Just wanted to kind of show that connection, how we're going to get from here to this arc length formula. So dividing by dx dt squared, or something as multiplying by dt squared over dx squared. And then we're able to put this together here. So if we were to take this piece and replace that, initially there was a dx, but then we have this dt squared over dx squared, which if we pull out of the radical, it'll become dt over dx. Dx's cancel out, and then now we have something that is coming from function form for arc length into parametric form. So arc length in parametric form when there's a time component. So basically, it is still involving f prime. We're just breaking that f prime down into its horizontal and vertical components, into its x and y components. So if there is, if your x and y are both defined in terms of time, then we just define dx dt, square that, dy dt, square that, and put it under square root. Okay, so today we're just practicing working through this formula today. Okay, so for number one, for each set of parametric equation, find the arc length of the curve. So now x and y are defined with this third variable, time. And we're trying to find the length of this curve when time is producing the curve between 0 and 2 pi. Okay, so we're going to find x prime. X prime will represent your dx dt. Y prime will represent your dy dt. Okay, our bounds from a to b will be from 0 to 2 pi. And the square root of x prime squared. And then cosine squared. Okay, what does this remind you of? Sine squared plus cosine squared equals what? Equals 1. Yeah, so that makes this a lot cleaner, a lot easier to work with. We know 1, square root of 1 is still 1. We take the antiderivative. This is in relation to time, so we know 1 becomes 1t. Now we can work in our upper and lower bounds. So that 2 pi, the reason that we're getting 2 pi is because if we were to graph this cosine and sine over the course of 0 and 2 pi, it's going to create basically a circle centered at 0, 0 with a radius of 1. And basically the circumference of a circle, the arc length around the circle is 2 pi r, radius is 1, and that's why we're getting that 2 pi. Okay, number 2. X and y are defined in terms of time. Okay, same idea here. We're just putting into our formula here. Our bound is from A to B, provided here with our domain. Okay, root 65 is just the constant. We tack on that degree 1. We know antiderivative, our degree is always going to rise by 1. So constant turns into a degree 1. And now we're ready for our bound. Okay, next page. Yeah, so today we're just going to practice, see how much we can get through between page 17 and page 18, and just practicing this process. So let's start on page 17. Okay, let me write the formula up here just for reference. Okay, so go ahead and start, and I'll show the solution to each once you guys had a chance to look at each problem. On the test, you get to use your calculator, but I want to see all your steps. Like as if you didn't have a calculator, if you know what I mean. Okay, number two, A and B are constants, so you'll treat A and B like you would if it was a 1 or 2. Oh, and by the way, some of the pages got skipped over. I took out some of the multiple choice practice problems just to make the packet a little bit smaller. But I'll bring some of those problems back in test review or in review in our review packet. But so that's why, yeah, pages are missing because I removed the multiple choice practice problems. Okay, so there's no need for product rule here. We're going to treat that a over 2 as just some coefficient in front. Power rule is only going to be required for that t squared. Same thing here. B over 2 is just some coefficient in front. T squared takes the derivative process. Okay, so we have x prime and y prime, and we're just putting into our Arclin formula. So what we can do here is we can try to factor out that t squared. It's really, we know that ultimately, that a and b are just numeric values. If I can just get that t squared to come out. So here, these are being multiplied. I can pull that t squared out as what? Just t. So all this, whatever's inside that square root is just going to be a numeric value. So we'll just treat that like just an extended coefficient, and really only have to involve the integral for t because all this is just a numeric coefficient in front. So we can keep that root a squared plus b squared as a number in front, and then just worry about antiderivative for t. So t becomes t squared over 2. Now we have our antiderivative. We can work in the bounds from 0 to 1. And 0 and 1 is only plugging in for t. The a and b are still unknown constants, so they will stay with our answer. And when I plug 0 in, that's going to zero this whole thing out. Okay, for number 3, we're going to clean things up, but we may have to go through a little bit of U substitution once we get everything situated. So go ahead and start number 3. factor out a GCF and see if we can somehow pull something out of the radical. Now that we have that 4t squared factored, we can also recognize that's a perfect square. I can pull that 4t squared out of the radical as 2t. Sorry. Write this. And this, look at how this is set up here. We can use what? With this process. We can rewrite this and let this be what? Yeah, we can let that be u. If we let our u value be 4 plus t squared, the derivative is 2t, and that should handle that 2t that we have in front. All the t's cancel out. We're just left with u to the 1/2. We can apply a power rule. Okay, bring back your original variable. Now we can involve the bounds. And then once you plug in the bounds and get everything in terms of a numeric value, we can stop. We don't have to clean up any further beyond that. Squared 20. Whatever that decimal value is, would be the arc length of this graph between 1 and 4. We know the sine squared plus cosine squared, which is reduced to 1. And the root 25 is just 5. So we're able to get it all the way cleaned up to just 5d theta. Okay, number 5. Okay, page 18. Okay, let's see if we can work through 6 through 10 on page 18.
Yeah. Yeah. Because it's hard, but things are down. In general, take training. Actually, you can really be decorated. Not me, so that happens. But that was it was the
Hey guys, the classwork is just going to be page 17 and 18. I think it's short enough where we can finish it in class. And I like to just be able to check your classwork grade at the end of class. Okay.
No. Pretty hard to get worse. Wait, hey, how do you do?
But you're following. Okay, we'll go to the top today. That's all I know. Combined babies, so we're trying to do. Really? Kind of everything. Or
Yeah, you have to do it. You see for
Good idea. Oh, really good. So,
I would say.
Yes. Which one would you rather be Miss Ready? Miss Louise?
Wait, you were there.
That's like what? We're live. What was it? Okay, wait, I
Like switching back.
Yeah, I did. It's not so ridiculous. It's not ridiculous. First.
Yeah, well, what they
Women invest at the same rate. Absolutely. He's like, she goes on a trend. Oh, yeah, but it's a David. You guys can hear this much. It's definitely not. It's a good straight target.
I was like, or now. I was like, obviously it's never. I mean, if you say so, like, I mean, like, I'm not gonna. Yeah, like, otherwise. That was bad. And that's what she started saying. Stay for a hug. And then he brought my house and be like, and then right? Yeah, guys. Yeah, I know. He's like, he's checking the one.
So dog or dog walker?
Yeah, I'll come around in 5 minutes to check you off on page 17 and page 18.
He's actually with, bro. Yeah, he's actually with. And I said, trust it. He's a trust. I know it's my. He's like, he's on the lead. I'm like, almost. He's so cute. My brother saw it. He's I still love that. Are you serious? I got us to make fun of it. Like, I should personally.
Guys, before I come around, let me just talk about the potential plan for next week. Guys, so there's a good chance that we may have remote days next week. So let's say Monday and Tuesday we're just going to be remote days. What I would like to do is to be able to just have a Teams lesson over the next two sections. But the good thing is these next two lessons with vectors are going to feel very much like parametric. And so I think it's pretty easy to pick up. And it's nice, hopefully, that we can have in-class time when we get into polar, because polar is what's that's going to require more time to get used to. So I'll send out a remind link to that Teams lesson. So right now, my tentative plan is BC Calc. I'll do a Teams lesson from 9:30 to 10:20. Monday, going over 9.5, and then 9.6 on Tuesday, 9:30 to 10:20. It'll be a live lesson, but if you can't join or you want to check out video later, I'll have it recorded. And then you can go through the pages and go through the classwork, homework, and work the problems. Okay. Yeah, so I think we'll probably hear more Saturday and Sunday what the plans are going to be for next week. Any questions? Okay, all right. Let me check your 2 pages. Okay. All right, I'll check.
Did you do that?
I like. Yeah. Oh, that's up to date. Oh. Just like the best in the world. That's why I
Are we behind on the first day? Because you missed the first day. Oh, nice.
love, yeah, for, and like, in my. Like I can't.
You can show how much you like. Sorry.
Like, let's go back to my one year.
Yeah, because less than me. So I'm already like so hard.
At some point, it's like not boring. Like if you don't like, you don't.
Do it.
I just take 5 years.
Hard. So.
So